Okay, good afternoon, everybody, or good morning, or good evening. It's a pleasure to have here today Professor Giovanni De Micheli from EPFL Lausanne, Switzerland, to talk about democratic circuits for a safe and greener tomorrow. So Professor De Micheli is a professor and director of the Integrated System Labs at EPFL Lausanne in Switzerland. Previously, he was professor of electrical engineering at Stanford University. So by the way, one of the former students of De Micheli was the founder of Yahoo. No. Yeah, so there is a lot of history about. So Professor De Micheli is fellow of ACM and IEEE, a member of the Academia Europaea and International Honorary member of the American Academy of Arts and Science. His current research interests include several aspects of design technology for integrated circuits and systems, such as synthesis for emerging technologies. He is also interested in heterogeneous platform design, including electrical components and biosensors, as well as in data processing of biomedical information. He is author of Synthesis and Optimization of Digital Circuits book with McGraw-Hill. He is co-author and or co-editor of 10 other books and of over 850 technical articles. His citation index is 97, according to Google Scholar. He is member of the Scientific Advisory Board of IMEC in Leuven and STMicroelectronics. Professor De Micheli is the recipient of the 2019 ACM SIGDA Pioneering Achievement Award, the 2016 EDAA Lifetime Achievement Award, the 2016 IEEE Computer Science Harry Goode Award for seminal contributions to design and design tools of network on chips, the 2003 IEEE Emanuel Piore Award for contributions to computer-aided synthesis of digital systems. And he received also the David Pederson Award for the best paper on the IEEE Transactions on CAS in 87 and 2018, and several best paper awards, including DAC in 83 and 93, DATE 2005, Nanoarch 2010 and 2012, and Mobile Health 2016. So this is just a short version of the larger CV with a lot of achievements that Professor De Micheli has in his career. So it's an honor for us to have here today Professor De Micheli to give this talk. So thank you very much again, Professor Giovanni De Micheli, to accept our invitation.
Okay, thank you very much, Ricardo, for inviting me. You have really a great list of speakers. I'm very honored to be one of the speakers in this series. I would like to thank the audience, their patience. I apologize for the delays in connecting. And I would like just to get into my talk. I'll give an outline first. I will have a brief introduction. I will give some current technology trends as we approach the end of the CMOS scaling. I'll talk about the majority paradigm in logic synthesis, and then I'll conclude the talk. I've used a fairly provocative title. I've used it because we are living in interesting time, if not dangerous times, because the three world powers have an authoritarian government. And where authoritarian means that leaders use the power of a person, of an elite, to run the country. And it's been shown in science, it is a scientific fact that large systems, whether they are social, economical, or engineering systems, benefit for having inputs that equally come from various parts. Stability of large systems requires equality of influence of its constituents. In the next part of the talk, I will restrict myself to electronics, and I will build on the notion that it's useful to have inputs from various parts of the circuits to determine and output, even for logic functions. Let's take, for example, CMOS circuits that we know very well, and let's see how decision-making is done in these circuits. Now, CMOS are extension, CMOS gates and the Inver gates are extension of NANDs and NORs, and decisions are based on the so-called controlling signals. For example, a single false input forces a NAND output to be true, and a single true input forces a NOR output to be false. Conversely, if you look at some emerging technologies, these technologies will enable us to vote, for example, by using majority logic functions or threshold logic gates, which, by the way, threshold gates realize weighted majority decisions, and threshold gates are an abstraction of what happens in our brain. Now, all these principles are not new, but the design methods are. And majority and threshold gates can be realized in CMOS, and that's very important in order to get better circuits. So what is majority logic? A majority logic circuit is a circuit that has an odd number of inputs and that returns the value true if the majority of inputs are true. People use often majority of 3, but everything that's based on majority of 3 can be extended to majority of n, where n is an odd number. There are new EDA tools for majority design. They give very good results when applied to CMOS, and they can be applied to emerging technologies. By the way, majority is the native abstraction for optical computing and wave computing because waves interfere, and when you have multiple waves, their output will construct or disrupt according to majority rules. And majority is also the native abstraction for superconducting electronics, and I will talk a little bit about that. So let me give you a quick review of some of the current technology trends. In CMOS, we have seen FinFETs, we have seen nanowires, we have seen nanosheets that can be seen as vertically stacked horizontal nanowires. We've also seen the possibility of building gates that have 2 control gates that will allow you to program electrically a transistor to be a P transistor or an N transistor. This is also called electrostatic doping, and this will create basically a device that is a comparator activated switch, and this transistor will inherently implement the XOR function. This is just a picture of nanowires that have 2 gates for control. There's also been a recent strong interest on carbon nanotube transistors. Carbon nanotubes benefit from a higher mobility as compared to CMOS, and so you can push more currents for the same cross-section and be faster even if you scale down the geometries. Now, handling CNTs, it's difficult because of their nature, but recent research, especially at Stanford and MIT, has enabled the design of large circuits. This is a 16-bit RISC-V that's been achieved all in CNTs with about 14,000 CNFET transistors, and it was published last year on Nature. It's the work of Max Schulaker and co-workers. Interesting today, we have also 2-dimensional materials. This picture is a sketch of MOS2, which is molybdenum disulfide, which is a material that allows to build transistors that are particularly effective. This is not the only material that can be used in 2Ds. An interesting material is wolframium diselenide that allows also to build transistors that can be either P or N and controlled electrically. This is an example of an XOR gate in this technology, and this is an example of a small standard cell library that includes the majority gate. So what are the key points of these advances in technology? There are multi-gate transistors that have device-level programmability that are very interesting. They can realize native majority functions. And we can think of a paradigm where circuits are designed in terms of different primitives, different as compared to ORs and ANDs or NORs and NANDs. For example, you could use majority function as comparator and comparisons as the basis of design. And this actually is much used today in data path design, where you have many others and multipliers. Others are built out of majority gates and XOR gates. And as we see, complex systems that use, for example, machine learning engines, then implementing effectively addition and multiplication is extremely important. Let me say a few words about superconducting electronics, which is a very interesting technology. It was very popular until the 80s by computer companies like IBM, Hitachi, NECs. But then this technology fell behind CMOS because CMOS was scaling down very quickly. And nowadays, with the slowdown of Moore's law, superconducting electronics is getting, again, a technology of interest. The key elements in superconducting electronics are the Josephson junction, that is a junction that can switch from resistive to the superconductive state, as well as inductors. The operation of these circuits is typical at 4 Kelvin, so cooling efficiency is extremely important for this type of devices. There are various families of superconductors. The superconducting electronics has changed a lot as compared to the 80s. It used standard logic gates, but these gates are clocked, leading to heavily pipeline logic. One thing to remember is that superconducting electronics is quite different from quantum computing. In superconducting electronics, you have a chilled operation at 4 Kelvin to achieve superconductivity. In quantum computing, you need to operate at much lower temperatures, like 10 millikelvin, in order to reduce noise. And quantum computing builds upon the principle of superposition and entanglement, while superconducting electronics builds upon standard logic principles. But in superconducting electronics, there's a shared principle. Computation is done by using pulses, and these are current pulses that correspond to flux quanta. Various families can be distinguished because they can be driven by DC bias or AC power. That is, adiabatic computation is done within superconducting electronics. The major families, there are 2 major families of circuits of interest today. The rapid single quantum flux, which is due to the work of Likarev, and the current most recent families of interest are RQL, reciprocal quantum logic, as well as dynamic SFQ, developed by Kralov and E.B. Friedman. Another important family of superconductors is the adiabatic quantum flux parameter, where the name parameter relates to an oscillating circuit that stores 2 states. I'll give you just one example of circuits in the last family, AQFB, where majority gate is the native abstraction. Here in AQFP, you see a buffer. The buffer is implemented by several inductors and JJs, Josephson junctions. As an example, in the picture, you see that the current pulse coming from the top will make one of the 2 loops that you have superconductive, and as a result, you will issue an output pulse that can be inverted in the case you want to achieve an inverting buffer, but just reverting the couple of the bottom transformer that I have in the gate. But what is most important is that once you have a buffer, you can build majority gates by combining buffers, because the output pulses can be added and subtracted. So this is the basic majority gate that consists of 3 buffers next to each other, attached to a join gate, where the join is an abstraction of several inductors and small transformers that can be integrated. This is an example of another function where you do the majority of A, the complement of B and C, where you use an inverter buffer in between. And this is an example of an AND gate, which is obtained by modifying a majority gate by having a buffer that yields the constant 0 as a pulse. Key points of this. Superconducting electronic gates can be abstracted as majority. This is the native abstraction. Currently, majority 3 is used, but recent technologies like dynamic FSQ can exploit wider majority gates. Optimizing majority logic network is key into this, and some families require explicit inverter realization, some families do not. Buffering is also essential in this type of technology. You need to buffer in order to have capability of sending pulses where you have high fan out, and this is complex because buffer trees may require an appropriate blocking, and the signals have to be kept in phase. There is a very low energy consumption per logic gates. Logic gates typically would consume 4 nanowatts per gate, but they still need refrigeration, and as a result, the refrigeration efficiency is extremely important. But fortunately, refrigerators for superconductors are improving quite fast today. So, as a result, what I want to say is that various circuit families, including superconductors, 2D devices, optical electronics, quantum cellular automata, can be modeled as majority functions. Let me come now to the second part of my talk, and I want to talk about the majority paradigm in logic synthesis, about models, algorithms, and tools. So, why is majority logic important? Majority logic has sound mathematical foundation, and it gives us an opportunity to design better and faster circuits. Majority logic synthesis tools are also effective for CMOS design. They've been shown to give circuits that are competitive. And also majority gates can implement threshold functions, as I said before. Most importantly, quoting Donald Knuth in the last book, The Art of Computer Programming, Volume 4A, he says that the majority of 3 inputs is probably the most important ternary operation in the entire universe. This is a very strong statement by Donald Knuth, and I believe that it's true because there are many properties of majority that are being discovered and rediscovered. So again, why majority logic? Majority is a powerful generalization of ANDs and ORs. You can make an AND gate or an OR gate by using a constant as an input to a majority gate. Majority logic unlocks optimization opportunities that were not apparent before. For example, here you see a circuit realization of a function in terms of ANDs and ORs, and here you will see the same realization in terms of 2 majority gates. Well, it's easy to argue that being majority a more complex primitive, you would need fewer gates. But what is important to see is what happens after having done technology mapping. So here we pick up a library which is fairly common. It's the general library from MCNC, and we see the 2 realization that we had before. This is a mapping. In one case, that's a mapping with majority gates, and here you will see the area and the delay. The area decreases with majority gates. The delay will stay constant. But if we add the complement of the majority gate, that is the minority 3 gate, to the library, then you have an implementation that has both smaller area, and smaller delay. Well, of course, this is a very small example, and one has to validate these claims on bigger circuits. So how can we exploit majority logic in large circuits? We want to have a good and scalable method for manipulating majority. Nowadays, the state of the art is mainly using AND/OR inverter gates, as in the tool ABC, and using traditional Boolean algebra axioms and theorems to manipulate these AOIGs. For majority, we use instead a different abstraction, which is the MIGs, the majority inverter graphs, and the corresponding new Boolean algebra to deal natively with majority and inverters. So what is a majority inverter graph? It's a logic network that consists of 3 inputs majority nodes and regular or complemented edges. Complemented edges have a bubble and actually show the inversion. Properties of these MIGs. All AND/OR inverter gates can be transformed into MIGs. Why? Because a majority gate can implement the AND or the OR function by having an input set to 1 or to 0. And in the right picture, you will see a 1 which gets complemented. So MIGs include AOIGs and also include just AND inverter graphs. The properties of MIGs can be expressed in terms of a Boolean algebra which builds on 5 axioms. Commutativity, that means that no matter when you vote, your vote counts the same. Majority, that means that if 2 inputs are the same, they win if there are 3 voters. And then associativity and distributivity, as well as inverter propagation. Now, the majority function is self-dual. That is, if you complement the inputs, you get the complemented output. What is important to state is that the Boolean algebra subject to this object that implements this axiom is a Boolean algebra. From a more formal point of view, the Boolean algebra with the axioms that I've shown is both sound and complete. Sound, it means that if a formula is derivable from omega, then it's valid. And complete means that each valid formula is derivable from the axioms omega. Why is this important? This is important because you have the reachability property in MIGs. That is, any MIG configuration is reachable from any other equivalent MIG configuration. What are these configurations? Suppose that you are doing logic synthesis. At some point, you have one interconnection of your primitives, and you want to go to another one. There is always a path that will connect 2 configurations of a logic network. That is, there is always a path that will lead from the current configuration at hand to the global optimum for the circuits in terms of area or delay. Now, the fact that there exists a path doesn't mean that it's easy to find this path. This path can be exponentially long or could be hard to find, but at least there is a proven reachability inside the state space. Now, how do you do optimization of MIGs? Well, you do it by using the axioms, and MIGs can be optimized by going through stepwise transformations. What you care about? You care about reducing the area, that is, reducing the MIG size. You care about reducing the delay, which correspond to reducing the depth of an MIG. And you care about reducing the power, that relates to reducing the switching activity of an MIG. Let me give you some examples. How would you reduce the number of nodes in MIG? You could use, for example, the majority property that can simplify basically a majority gate into a connection. Or you could use the distributivity property that, if you apply it from right to left, will allow you to remove one majority gate from the circuit. What about depth optimization, that is timing optimization. You could use again the majority axiom that will allow you to remove a majority gate, or you could use, for example, the associativity property in one or the other direction. Well, what is important there? It's important what is the latest incoming signal, and according to the latest incoming signal, you can restructure, you can rewrite your network in order to have a more performing one. Let me give you an example with others. Here you have a sketch of an adder in terms of AND/OR and inverters. This is the realization in terms of mix. The number of levels goes down if you're trying to optimize for delay. Actually, what's interesting is that the transformation on MIGs allow you to find out a carry look ahead structure in more or less an automatic way. Keep in mind that here these techniques are still based on heuristic choices of the transformations that you applied in rewriting your MIGs. So you're not guaranteed to get the best. But still, it's interesting that for many others that are known, this type of technique can lead to structure that has a depth which correspond to the best one known, where best means by doing manual design, and others are very well-known structures. Everything that we've seen up to now relates to using the algebraic properties in terms of rewriting, but you can also do Boolean optimization of MIGs. And this is a way to exploit the Boolean nature of MIGs, because an MIG is fundamentally a hierarchically majority voting system, where at each level you vote based on the outcome of the votes at the previous level. Now, this type of majority voting can correct various types of bit errors. What are these bit errors? These are simplification that you can do in part of the network in order to make it smaller or faster, and then you can use the majority function in order to correct this reduction so that you have the correct output. So in other words, you can put some logic errors in some smart places, and as long as the errors that you introduce are orthogonal in the entry point of the top majority level, this is allowed. This gives you a correct output. So this allows you to apply Boolean transformation to reduce subnetworks that would fit into a majority gate. Now, how is majority synthesis implemented? It's been implemented inside a tool called MIGHTY that was developed by Luca Maru at EPFL, and it's been applied to various types of benchmarks, starting from the classic logic networks benchmarks, the MCNC ones, and going up to the larger combinational arithmetic logic units. This picture here summarizes some of the comparisons of the MIG optimization to the AIG optimization in ABC and BD-based optimization. In a few words, we can say that MIGs and AIGs do better than BDDs. The size of MIGs and activity is comparable to the one of AIGs, but MIGs allow to reduce the depth about 20% with respect to AIGs. Now, what about applying this to large-scale circuits? So an experiment's been done by using circuits mapped to a 22 nano CMOS libraries, and MIG has been used as a front end to logic synthesis and physical design. So the experiment consists of taking the benchmark, passing them through a commercial tool set, and then doing the same, but where the benchmarks have been pre-optimized by using MIGHTY. And the results show a reduction of 15% in terms of delay, 5% in terms of area, and 2% in terms of power when using a script that favors depth optimizations. Now, all circuits underwent formal verification with success. Now, a similar experiment has been done on an IP block, a divisor. Again, MIG was used as a front end, and the summary of the result is that area has been slightly reduced, delay has been reduced by 15%, and gate count has been reduced as well on this type of circuit, which is a well-known IP block. Now, what about using nanotechnologies and majority design? Well, some experiments have been done on a spin wave device. Again, I don't want to read to you the entire table, but I can show you the final bottom line on this table here, which is the average delay. And using the MIG technology, again, about a 20% delay reduction has been done. And I would like to mention also a design of a block using a silicon nanowire double gate technology. It's again the divisor, and showing you what were the final results. In this experiment, the area has increased, but the delay was decreased by 15%. This shows that these methods not necessarily do well with respect to all the objective functions, but they can do well in terms of doing delay reduction. So what are the key points? Key points is that majority inverter graphs with their Boolean algebra push further the capabilities of modern logic synthesis. You can have significant improvements for general benchmarks, but also for highly optimized units. And there's support for emerging nanotechnology libraries. What I would like to add on top of what I said in terms of results, which is a recent achievement, is that the majority logic optimization has been implemented within a commercial tools, and that has given better results as compared to MIT, better especially in terms of area recovery, while achieving results that are better or equal to the one obtained by MIT. So let me come to a conclusion. I would like to go back to the big picture. If you look at the circuits as we see today, especially circuits that are related to sensors that are implemented within embedded systems, these circuits benefit from averaging data captured by sensors. Using multi-input can lead you to have an overall safer operation. At the same time, we have this very strong requirement today to reduce energy consumption of circuits, and it has been shown on CMOS that using majority optimization, you can achieve the same performance with lower power consumption profiles. So majority optimization is useful for reducing power, and it's also a key asset for emerging technologies such as superconducting electronics that can be used to do complex operations with very small consumption per gate. Of course, we have to create tools that enable the design of large superconducting circuits, because that will be only by using large circuits that you will see the gain in terms of power consumption, when you have to take into account that the circuits have to be refrigerated. In conclusion, new design, synthesis, and verification methods stem from new abstractions of computing devices. So it's always important to look at the circuits, model them, and be bold in using new abstraction, new model, new methods, especially because optimization is based on heuristics. Experimentation is extremely important, and it's also very important to be able to change the primitives and the structure of optimization tools. In general, I would like to stress that to achieve top performance, you need both technology and design, as well as a good match between them. I would like to thank you for your attention. I would like to thank my research group that helped me in addressing some of the problems that have been described today. I would like to apologize for delaying starting the talk and for being a little bit rushed in my presentation. Thank you again.
Thank you very much, Nani. So, for questions, please put your questions in the YouTube channel. So I have a question from David Harvey from Liverpool, UK. So the question is, what is Giovanni's view on quantum technologies and possible progress advance?
I didn't talk about quantum computing. I think that quantum technology is very important. Quantum computers will not be general purpose computer, but can be seen as accelerators. And in specific domain, these accelerators can be very useful. Already today, Microsoft is used in their program Azure quantum computing to accelerate imaging. Now, one of the big issues there are two major issues in quantum computing. One is to build a reliable technology. And that's important because still today, the coherence time are very short. And so it is impossible to run computer task or programming task of a certain length of quantum computers. And you need to do error correction, which is extremely painful. I'm not working on technologies for quantum computing, so I cannot say anything further than that. But I like to stress another point that I know well. You need to have logic design and logic design flows for quantum computers. That is, tools that allow you to map a description of an algorithm in a quantum programming logic, in quantum programming language, down to quantum gates. And that's a very important technology that's being developed today, but it's not yet ready.
Okay, thank you. So if you have the audience have more questions, please do it as soon as possible. So I have one question. Do you have some example of industrial circuits that are using majority gates?
Well, majority gates per se are used within all circuits that have adders and multipliers. That is inside the CMOS chip that are designed today. In terms of standard, let's say, random logic, majority gates are used as a tool to optimize the logic. They may be mapped to something else because some libraries include the minority gate in CMOS. Some libraries do not use it. So majority gates may end up in an inverted way in some part of the circuits, in some realization, and some other not. To be actually frank, I think that what is really interesting is to see the entire ensemble of 3 inputs gates, not just majority, but as potential primitives. This as compared to 3 input ANDs and 3 input ORs that we know very well. So it's the general issue is how can we use different bases for technology-independent logic optimization. And majority has been shown to be effective as really optimizing circuit that then would be mapped to a library.
Okay, so about this, the majority gates you use in your examples, you took from a library, or how you have done the layout of these majority gates?
In the circuits where I was talking about the experiments, the place and route was done with a standard library. It was done with a commercial tool, so I cannot mention the company and the library that was used. but eventually the circuits were mapped to the elements of that library.
Okay, so we have a question here by Clovis Fingenbaum. You said that that majority logic implemented on chips generate faster answers. So could you tell if this is used in avionics for faster decision and redundancy?
Well, in avionics, avionics does use triple modular redundancy and use majority voting in order to determine if a unit is not working properly. And this is done at various levels of the hierarchy. It's done as a way as checking the operation of computing engines, and also within computer parts, within processor, using avionics in order to check if a part is faulty or not. Majority is quite used in that.
Okay. So thank you very much. I think there is no more questions. Take care, everybody.